Hello and welcome. In this video, we'll be diving into the world of logarithms. By the end of this session, you will be able to define logarithms as the inverse of exponential functions, convert between logarithmic and exponential forms, and solve basic logarithmic equations. We'll start with a classic problem to see why logarithms are so useful. Imagine a population of 1,000 mice that doubles every week. The population after t weeks is given by the exponential function p of t equals 1,000 times 2 to the power of t. Now, a natural question arises. How long will it take for the population to reach 20,000 mice? To find this, we need to solve the equation 20,000 equals 1,000 times 2 to the power of t. First, we can simplify this by dividing both sides by 1,000, which gives us 20 equals 2 to the power of t. This equation asks, to what power must we raise 2 to get 20? We know that 2 to the power of 4 is 16, and 2 to the power of 5 is 32. So, the answer, t, must be somewhere between 4 and 5. But how do we find the exact value? This is where logarithms come in. Let's begin with logarithms in base 10. Our objective here is to understand the relationship between exponential functions and their inverse, the logarithm. Consider the exponential function f of x equals 10 to the power of x. Its inverse function, f inverse of x, is defined as the logarithm in base 10 of x. Remember that inverse functions essentially undo each other. If we start with x, apply f, and then apply f inverse, we get back to x. This means that if y equals 10 to the power of x, then x must be the logarithm in base 10 of y. So, the statement y equals 10 to the power of x is equivalent to the statement x equals log base 10 of y. This is the fundamental definition of a logarithm. In other words, the logarithm in base 10 of a number is the exponent to which 10 must be raised to get that number. It answers the question, 10 to what power equals this number? For example, since 1,000 equals 10 to the power of 3, the logarithm in base 10 of 1,000 is 3. Similarly, since 0.01 equals 10 to the power of negative 2, the logarithm in base 10 of 0.01 is negative 2. A common convention is that if no base is written, it is assumed to be base 10. So log of a means log base 10 of a. It's also crucial to note that the number inside the logarithm, which we call the argument, must be positive. This is because 10 to any real power is always a positive number. You cannot take the logarithm of a negative number, or 0. Let's look at a key property that comes directly from the definition. If we have log base 10 of 10 to the power of x, the answer is simply x. This is because the logarithm and the exponential function are inverses. They cancel each other out. This property is incredibly useful for simplifying expressions. Let's work through an example. Our goal is to find the value of a logarithm without a calculator. Let's find the logarithm of the fourth root of 10. First, we rewrite the fourth root of 10 as a power of 10. The fourth root is the same as raising to the power of 1/4. So we have log of 10 to the power of 1/4. Now, using our property log base 10 of 10 to the power of x equals x, the logarithm and the base 10 cancel, leaving us with just the exponent, 1/4. So log of the fourth root of 10 is 1/4. We have now defined logarithms in base 10 as the inverse of the exponential function 10 to the power of x, and we've seen how to use the property log base 10 of 10 to the power of x equals x to evaluate expressions. Now, let's generalize this concept to logarithms in any base. Our objective is to define logarithms in base, a, and understand the relationship between the logarithmic and exponential forms. Just as log base 10 is the inverse of 10 to the power of x, the logarithm in base, a, is the inverse of the exponential function f of x equals a to the power of x. This means that if y equals a to the power of x, then x is the logarithm in base a of y. The logarithm in base a of a number is the exponent to which the base a must be raised to get that number. This is the key relationship, b equals a to the power of x if, and only if x, equals log base a of b. These two statements are interchangeable. There are a couple of important conditions for this definition. The base, a, must be a positive number and not equal to 1. Also, the argument b must be positive. Let's look at some examples. The statement 8 equals 2 to the power of 3 is equivalent to the logarithmic statement 3 equals log base 2 of 8. They both express the same relationship between the numbers 2, 3, and 8. From this definition, we can derive two more fundamental properties. First, log base a of a to the power of x is x. This is the same inverse property we saw with base 10. The logarithm and the exponential function with the same base cancel each other out. Second, a to the power of log base a of x is also x. This is the other direction of the inverse relationship. The exponential function and the logarithm with the same base cancel each other out. Let's practice converting between these forms with an example. Let's find the value of log base 2 of 16. We are looking for the exponent to which we raise 2 to get 16. We know that 16 is 2 to the power of 4. So we can rewrite the expression as log base 2 of 2 to the power of 4. Using our property log, base a of a to the power of x equals x, the answer is simply 4. So log base 2 of 16 is 4. Let's try another one. Find log base 5 of 0.2. First, let's write 0.2 as a fraction, which is 1/5. Then we can write 1/5 as 5 to the power of -1. So we have log base 5 of 5 to the power of -1. Again, using our property, the answer is the exponent, which is -1. So log base 5 of 0.2 is -1. We have now successfully defined logarithms in any base, a, and practice converting between exponential and logarithmic forms to evaluate expressions. In this section, we will explore the powerful laws of logarithms. Our objective is to learn and apply the three main laws of logarithms to simplify and manipulate logarithmic expressions. These laws are derived directly from the laws of exponents, which you are already familiar with. Let's state them first. For any base c, where c is positive and not equal to 1, and for any positive numbers a and b, we have three laws. The product law states that the logarithm of a product is the sum of the logarithms. The quotient law states that the logarithm of a quotient is the difference of the logarithms. And the power law states that the logarithm of a number raised to a power is the power times the logarithm of the number. Let's see these laws in action with some examples. Our goal is to write expressions as a single logarithm. First, let's simplify log base 3 of 24 minus log base 3 of 8. This expression involves the difference of two logarithms with the same base. We can use the quotient law, which says that the difference of logarithms is the logarithm of the quotient. So we write this as log base 3 of 24 divided by 8. Simplifying the fraction, we get log base 3 of 3, and we know that log base 3 of 3 is 1, because 3 to the power of 1 is 3, so the entire expression simplifies to 1. Let's try an example that combines the power law and the quotient law. Simplify 2 times log of 7 minus 3 times log of 2. First, we apply the power law to both terms. The coefficient becomes the exponent, so 2 log 7 becomes log of 7 squared, and 3 log 2 becomes log of 2 cubed. Next, we evaluate the powers. 7 squared is 49, and 2 cubed is 8. So we have log of 49 minus log of 8. Finally, we use the quotient law. The difference of logarithms is the logarithm of the quotient, so the simplified expression is log of 49 over 8. Let's look at one more example that involves a constant. Simplify 2 times log of 3 plus 3. First, apply the power law to the first term. 2 log 3 becomes log of 3 squared, which is log of 9. Now, we need to express the constant 3 as a logarithm in base 10. We know that 3 is the same as 3 times 1, and 1 is log base 10 of 10. So 3 is 3 times log of 10, which by the power law is log of 10 cubed, or log of 1,000. Now we have the sum of two logarithms. Using the product law, we multiply their arguments. 9 times 1,000 is 9,000. So the simplified expression is log of 9,000. We have now learned and applied the three main laws of logarithms: the product, quotient, and power laws. These laws are essential tools for simplifying and solving logarithmic equations. In this scene, we'll focus on a special type of logarithm called the natural logarithm. Our objective is to define the natural logarithm and understand its properties. The natural logarithm is simply the logarithm in base e. The number e is a fundamental mathematical constant approximately equal to 2.71828. It arises naturally in many areas of science and finance. We use a special notation for the natural logarithm ln of x, so ln of x is just a shorthand for log base e of x. Just like with base 10 logarithms, the natural logarithm is the inverse of the exponential function with base e. This means that if y equals e to the power of x, then x equals the natural logarithm of y. It answers the question, e to what power equals this number? This inverse relationship gives us two key properties, identical in form to the ones we saw for base a. First, the natural logarithm of e to the power of x is x. Second, e to the power of the natural logarithm of x is also x. These properties are crucial for solving equations involving east and ln. Let's use these properties to evaluate some expressions without a calculator. First, let's find the natural logarithm of e squared. Using the property ln of e to the power of x equals x, the answer is simply the exponent, which is 2. Next, let's find the natural logarithm of the square root of e. First, we rewrite the square root of e as e to the power of 1/2. Then, using the same property, the answer is the exponent, 1/2. Finally, let's find e to the power of the natural logarithm of 3. Using the property e to the power of ln x equals x, the answer is simply 3. We have now defined the natural logarithm as the logarithm in base e and seen how to use its inverse properties to evaluate expressions. The laws of logarithms we learned earlier apply equally to natural logarithms. In this scene, we'll apply the laws of logarithms to solve equations. Our objective is to use the properties of logarithms to solve for an unknown variable. The key principle here is that if the logarithm of one number equals the logarithm of another number, and they have the same base, then the numbers themselves must be equal. This allows us to cancel the logarithms. So if log base a of m equals log base a of n, then m must equal n. This is a powerful tool for solving equations. Let's work through an example. Solve for x in the equation log base 5 of 125 minus log base 5 of the square root of 5 equals log base 5 of x. First, let's simplify the left side of the equation. We have the difference of two logarithms, so we can use the quotient law to combine them into a single logarithm. Now, let's simplify the argument. We can write 125 as 5 cubed, and the square root of 5 as 5 to the power of 1/2. Using the laws of exponents, we subtract the powers. 3 minus 1/2 is 2.5, or 5 over 2. Now we have log base 5 of 5 to the power of 5 over 2 equals log base 5 of x. Since the logarithms are equal and have the same base, their arguments must be equal. Therefore, x equals 5 to the power of 5 over 2. We can write this in a more familiar form. 5 to the power of 5 over 2 is the same as the square root of 5 to the power of 5, which is 25 times the square root of 5. So, the exact solution is x equals 25 root 5. Let's try another example. Solve for x in the equation log of x plus 1 equals log of 30. On the left side, we have the sum of two logarithms. We can use the product law to combine them into a single logarithm of the product of their arguments. Now we have log of x squared plus x equals log of 30. Since the logarithms are equal, their arguments must be equal. This gives us a quadratic equation. X squared plus x minus 30 equals 0. We can solve this by factoring. The factors of minus 30 that add to 1 are 6 and minus 5. So the equation becomes x plus 6 times x minus 5 equals 0. This gives us two potential solutions, x equals minus 6 or x equals 5. However, we must check our answers. Remember that the argument of a logarithm must be positive. If we substitute x equals minus 6 into the original equation, we get log of minus 6, which is undefined. So x equals minus 6 is an extraneous solution. If we substitute x equals 5, we get log of 5 plus log of 6, which is valid. So the only solution is x equals 5. We have now seen how to use the laws of logarithms to solve equations by combining terms and equating arguments, and we've learned the importance of checking for extraneous solutions. In this scene, we'll tackle exponential equations where the bases cannot be easily made the same. Our objective is to use logarithms to find the exact solution to these equations. The key idea is that we can take the logarithm of both sides of an equation. This is a valid operation as long as both sides of the equation are positive. Let's revisit our opening problem. 2 to the power of t equals 20. We couldn't solve this by inspection. Now we can. We take the logarithm of both sides. We can choose any base, but base 10 or base e are convenient because they are on our calculators. Let's use base 10. Now we apply the power law of logarithms to the left side. The exponent t comes down as a coefficient, so we have t times log of 2 equals log of 20. To isolate t, we simply divide both sides by log of 2. This gives us the exact solution. T equals log of 20 divided by log of 2. Using a calculator, we find that t is approximately 4.32, so it would take about 4.32 weeks for the mouse population to reach 20,000. Let's try another example. Solve for x in the equation 3 to the power of x plus 1 equals 5 to the power of x. Again, we take the logarithm of both sides. Let's use the natural logarithm this time. Apply the power law to both sides. The exponents come down as coefficients. Now we have an algebraic equation to solve for x. First, distribute ln 3 on the left side. Next, gather all the terms containing x on one side. Let's move x ln 3 to the right side. Factor out x from the terms on the right side. Finally, divide by the coefficient of x to solve for x. This gives us the exact solution. X equals ln 3 divided by the quantity ln 5 minus ln 3. Using a calculator, we find that x is approximately 2.15. This method allows us to find the exact solution for any exponential equation. We have now learned how to solve exponential equations by taking the logarithm of both sides, applying the power law, and solving the resulting algebraic equation. Let's recap what we've learned today. We started by defining logarithms as the inverse of exponential functions. We saw that the statement b equals a to the power of x is equivalent to x equals log base a of b. We then explored the three fundamental laws of logarithms: the product, quotient, and power laws. These laws are essential for simplifying complex logarithmic expressions. We also introduced the natural logarithm, which is the logarithm in base e, and saw how its inverse properties with e to the power of x are used to simplify expressions. Finally, we applied these concepts to solve logarithmic and exponential equations, emphasizing the importance of checking for extraneous solutions and using logarithms to find exact answers. You are now able to define logarithms, convert between forms, apply the laws of logarithms, and solve basic logarithmic and exponential equations. To solidify your understanding, here are 5 practice questions. Take a moment to work through these problems. The answers will be provided on the next slide. Here are the solutions to the practice questions. Let's go through them one by one. For question 1, we first use the power law, then the quotient law, and finally evaluate the logarithm to get an answer of 3. For question 2, we use the product law, convert to exponential form, solve the quadratic equation, and discard the extraneous solution to find x equals 7. For question 3, we take the natural logarithm of both sides, use the power law, and solve for x to get the exact answer. X equals ln 12 over ln 5. For question 4, we rewrite the expression with a single exponent, then use the inverse property of the natural logarithm to get the answer 7 over 2. And for question 5, we take the natural logarithm of both sides, use the inverse property, and solve for x to get the exact answer. X equals ln 7 over 2. I hope this video has helped you build a strong foundation in logarithms. Keep practicing these concepts, as they are fundamental to many areas of mathematics and science. Thank you for watching.